Hello, everyone, and thank you for attending today's webinar about antenna principles in your network with KP Performance Antennas. This webinar is being recorded, and if there are any questions throughout the presentation, please go ahead and type them in the question box, and we'll get to them after the presentation is complete. Our presenter today is Justin G. Pollock, and he is a Senior Antenna Engineer at KP Performance Antennas and Radio Waves, where he oversees the product development of industry-leading technologies. He received his PhD in electrical engineering from the University of Alberta and has authored technical articles in the field of RF and microwave engineering, antennas, physics, and optics. Thank you, Justin, for being here today. I'm going to go ahead and let you take it away.
Thank you, Angela. Yes, so my name's Justin, and I'm with KP Performance, and I also manage new product development for Radio Waves too. So today we're going to talk just about KP. Let me just go to my next slide here. Just talk briefly about principles. Before I had a very long deck that goes over every aspect. We're going to go quickly through that so we can focus on some of the new fun things. Looking at comparing the horns that are very popular in the market and versus traditional sector antennas. Try to dispel some of the beliefs and hype around the horns, which some of it is warranted, but some of it goes a little bit extreme. And then also talk about some of our new products that we released. And then if we have time, I think we're going to talk about some which radios are compatible with which sector antennas. So without further ado, let's talk about antennas. You know what an antenna does? It takes your radio signal and it transduces it, that electrical signal, into an electromagnetic wave that propagates through free space. That's the technical term of an antenna's operation. But there's many different aspects of an antenna. I mean, we talk about what frequency it operates at, what its VSWR, gain. I mean, those are the very most important things, gain and frequency, and also size. How big is it, what temperature, what type of wind load does it survive, does it have ingress protection? Typically antennas don't have ingress protection, and if they do, take it with a grain of salt, because there's usually a drain hole in the bottom of them. And all types of different properties we need to talk about, but we're going to just focus here on the most important ones, and that has to do with how well or how the antenna radiates in free space. An antenna, what it does is it directs power from pointing it, instead of all directions, it points it into one direction. So it's a spatial distribution of the power, and this is just the typical 3D pattern. You can get it from any simulation software for a sector antenna. And if we just break this down into 2D cuts, which is what we're used to seeing, is instead of a 3D representation, we see a two-dimensional representation of this pattern. The first one we usually see is the azimuth cut. So here we're seeing an azimuth pattern. It's got a nice 65-degree 3 dB beam width, which I'm highlighting here. So that means half the power is contained within this arc in the 2D plane. Now, another important parameter here in the azimuth is a pattern skew or squint. You'll probably hear squint more, and here I'm exaggerating it, but it kind of tells you off the mechanical bore sight. So mechanical bore sight is directly in front of the antenna when it's level. So how far off the mechanical bore sight is the electrical maximum in the azimuth plane. So in the azimuth, you can see that the maximum azimuth pattern here is at 30 degrees. So that would be the pattern squint for this antenna. You typically only see this in multi-port antennas, 4x4, 8x8, 2x2. You don't see it too much, and it's tried to keep below 5 degrees. Elevation, very, very similar thing, except now the pattern's really squeezed down, and that's where you get the gain. If we have time, I'll talk about that a little bit later. But by squeezing the elevation pattern, that's what gets you that high gain in the sector antenna, and that comes from the length of it. So we see here that 3 dB beam width is about a 6 to 7 degrees. It's typical for sectors, anywhere from 6. Well, you can see 4, 6, 7, 8, and then if you're going very low frequencies, you get up to 15 degrees or so. And you can see here it's actually pointed down a little bit. So that's the electrical down tilt. This thing has probably about a 5-degree electrical down tilt. And so that means that the main beam in the elevation pattern is actually pointing towards the ground about 5 degrees, and that's good for getting coverage a little bit closer to the tower and avoiding interference. Another important parameter is the upper side lobe levels. Here you want to minimize these to minimize interference between cells or towers, and also it's a parameter called null filling. We don't hear it too much in our industry, but null filling is when you see right below the main lobe, the pattern goes really quickly down to small values. some antennas are designed to fill in this null. You're redistributing the power, and typically you compromise gain by doing that, but it allows you to get a little bit better coverage close to the tower. You see this coming up to like 15, somewhere between 15 and 20. You don't need very high values because, of course, we're providing coverage close to the tower, so the propagation distance is not very far. But when you have it going down to minus 30, it becomes a little bit of an issue. I already spent too long on this already, but here's how you measure antennas. One way to measure it. This is a near field anechoic chamber. It's a cylindrical scanner, and here's a sector antenna mounted on a fiberglass rod. And then this is a waveguide probe, and this just rotates around its axis, and then this stays fixed and measures the pattern. So gain is, like I said, one of the most important things to define an antenna. But what is gain? Gain is how we measure the absolute power that we receive and transmit from the antenna, and it's always relative to isotropic. So isotropic is if you had a point source. You remember back in physics class, if you have a point charge with plus q, it would radiate if it oscillated that point q to minus q back and forth at some hertz. It would radiate equally in all directions, so 4 pi steradians. Now, what ends up happening though is we introduce some type of structure to make the antenna directive. So directivity is actually taking your pattern in 3D and focusing in one direction. So that's directivity. It's just the focusing of the power. Has nothing to do with loss or anything. But once we start considering the loss in the antenna, any mismatch, material loss, whatever it is, then we get to gain. Gain is just directivity times antenna efficiency. Efficiency is always less than 1. So you can see that gain is always going to be less than directivity. So here I'm showing an example of 3 dB loss, which corresponds to efficiency of 50%. So typically for antennas, you can see efficiencies from anywhere from 10 to 20%, which are very low quality antennas, up to about 70%, I would say is max. Some very well-designed parabolic antennas can get higher, but those are for radar or space telemetry applications. You measure it with the NIST calibrated horn to make sure it's accurate. And here's here's the picture of the horn. And here's just some back of the hand calculations to help you kind of gauge, if I had this antenna, it's this certain size, operating at this frequency, what is the expected gain? Or you could say, I want this beam width in the azimuth and elevation. What is the expected gain of the antenna? They're just some first order approximations that allow you to just get a starting point to what you can expect from an antenna. Now, a very important spec that refers to very important in how we reuse frequency or your spectral efficiency is front to back. Front to back's a ratio of how much power is moving forward versus how much power is moving backwards, and we try to maximize the value as much as we can, get a high number. So here, apologies for the negative sign, but this is showing a 40 dB front to back, 40 dB. But really, it's only looking at comparing 2 angles, 0 degrees and 180 degrees. But there's a sector, if there's another sector behind here, you actually care, a little bit more on maybe the whole arc, plus minus 60 degrees, plus minus 45, plus minus 30 degrees, depending on what beam width of antenna this is. So a more accurate definition is to actually look at this arc right here in the red, and this is plus or minus 30 degrees. This is a base station antenna standard used by many of the antenna manufacturers that serve the cellular market. And they use this definition when they're defining front to back, and you see the front to back decrease from 40 to 33. But this is a more accurate representation of what you see in the field. This is what the sector behind it would see. Same with cross-pol. Cross-pol is a far field term. It's not port isolation, but it's kind of similar. But cross-pol is really the we try to radiate copol, which is the green curve here. So that's your desired polarization. I wanted to radiate H-pol, and I'm receiving H-pol on the other end, but you're going to end up radiating a little bit of the vertical polarization. That's the red, and you want to maximize the difference between the two. So looking at the definition here, if we just said at 0 degrees, oh, the cross-pol is 32, but really, I'm not using this sector just at 0 degrees. I'm using it over an arc, 60 degrees, 65, and I care about the cross-pol discrimination over this entire arc. So you look at the maximum value, and here we're at 18 dB, and this is the value that should be reported on the data sheet instead of just that 32, and it's a more accurate representation. So it's all about being careful how we read specs, questioning specs on data sheets, And always take everything with a grain of salt, because there's a lot of ambiguity in how we define things. It's not like a transistor, where you define combined voltage, current, or whatever very easily. There's a lot of give and take in how we define the specs. Now, slant polarization versus H and V, what's the difference? Like I said, polarization is a far field property. As the wave exits the antennas, it's polarized. That means the electric field in the electromagnetic wave is dominantly polarized in one direction versus another. So H and V, it's always with respect to ground. It's polarized like this, where V is away from the ground and H is parallel to the ground. Now, the difference with 45 slant is we just take that and rotate it 45 degrees. It actually provides a lot of benefits in the antenna side and also in the propagation side. So on the antenna side here, what we see is that the patterns become very symmetrical, and that's just due to the symmetry of the antenna itself. Where if you do H and V, there's an asymmetry introduced, and also just due to the physics of the antenna elements, that the H polarization will end up being a little bit wider beam width than the V polarization. I might have had those mixed up, but the key takeaway is there's different. And what does that cause? It causes chain imbalance in your signal. So H will come in hot +2, V will come in cold -2. And that can cause a little bit of havoc on your transceiver. Now it's got to lock onto the strongest signal or the weakest signal, and so you can get some saturation happening or not picking up the other signal above the noise floor. Now, another thing that's neat about ±45 is it propagates really nicely through non-line to sight applications. That's why in LTE and in a lot of cellular world, you'll see an antenna and it'll say it's 45 slants. They went away from H and V, that like the cellular guys, so your PCS, AWS bands, of many years ago, and just because they found that it propagates so much better in all these multi-pathing scenarios. Sorry. Now, what happens if you have a sector or that's H and V and a CP that's 45 slant? Well, theory tells us that the max mismatch drop in gain you're going to get due to the polarization mismatch is 3 dB. But since everything's multipathing, reflecting off trees, ground, even non-line of sight, you're going to get this just due to propagation through the atmosphere. That polarization is no longer H and V or 45 slant. It's somewhere in between. So you end up seeing a gain drop anywhere from a half a dB to 1 dB. It's not a complete wash, and a lot of the times, the higher gain antenna with 45 slant will end up overcoming this loss. So there's still, it's not, even if all your network is H and V, bringing in a 45 slant is not going to ruin your network, and in fact, you're probably going to increase the number of your capabilities just due to the benefits that you get through ±45 slant. Some technologies actually remove polarization mismatch, such as Mimosa's, their MIMO technology does that too. Now, quickly, how do you make a sector? All you do is you take in 10 elements. Here I'm showing a stacked patch, and you just repeat them in the vertical direction. And by repeating them and you connect them all together with your feed networks, you end up narrowing the beam from a nice wide beam width to narrower to, you get down to let's see here, 30 degrees elevation beam width, and then you go down to 8, you're at 7.6. So most antennas, especially at 5 gigahertz, 3 gigahertz, 2, is 8 elements, and that's why you get the beam width of 7.6. At 5 gigahertz, because of the extra higher frequency and lower wavelength, we can actually go up to 16 elements. We do this for our 90-degree sectors, and some at 3 gigahertz, we do this for 12 elements, and it allows you to get a nice narrow beam width and increase the gain just a little bit more. Now, caveat here is it's not a just increased number of elements, gain increases infinity, all the way up to infinity. There's a return happening where the efficiency ends up dropping a little bit as you increase the number of elements, just due to the feed network gets a little bit longer traces in there, and then it just drops the gain. But still, overall, the gain does increase. Now, that's antenna principles. I hope we 16 minutes, not too bad. You've gathered enough now to understand the basics of how a sector antenna works, and at least the basics of the azimuth and elevation beam width. But now I just want to compare the horns, which, like I said, it's a very popular tool, versus a sector antenna. Now, just very broad comparisons. If you compare a sector and a horn, sector is long and rectangular. A horn is elliptical or circular and smaller footprint. Now, size is everything here. So size gets you gain. So because the sector is longer in the vertical direction, it has a narrower elevation beam width and it gets a higher gain. Where the horn it's symmetric, so it has, or slightly asymmetric, so it has roughly equal azimuth and elevation gain. Now, there's a benefit for one or the other. You know, symmetric gain might be good for when you want to provide coverage maybe close in a tower or in a valley, but it's not going to end up propagating very far out, and also is going to have very large roll-offs, and let me explain that. So another major difference here in the sector and the horn is the beam width. So sectors are always defined with a 3 dB beam width, and that's this first dash blue curve here, the outer one. And we can see here that this is a 45-degree sector in the yellow arc. That covers 45 degrees right there. Now, let's go to the horn. What we're seeing with the horn definition is that their beam width on their data sheets are described with a 6 dB roll-off. Now take that in consideration. A 3 dB roll-off is half the powers contained in this arc. A 6 dB is 1/4 of the power. So if we're going to compare this horn to this sector, you can't compare a 30-degree horn to a 30-degree sector. You have, because the beam width definition is different. You have to compare a 30-degree horn with a 3 dB beam width of 30 degrees to a 45-degree horn, 30-degree sector to a 45-degree horn, which that 45 degrees is a 6 dB roll-off. And you can see here that if this is a 45, that it's not providing the same level of coverage as the sector here in the red zones, because the drop roll-off is so much more. So that's a very, very important caveat, and I'm just going to explain that a little bit more in the next slides here. So here I'm just comparing, we'll start with the symmetric horns, have been in the market for many years. A lot of people know and love them, but the sector is still a very good comparison against them. So here we're comparing a 45-degree sector versus a 40-degree and a 60-degree horn. And just reiterate here, the 45-degree sector is 3 dB beam width, and these are 6 dB beam widths here. So let's just focus here on the graph on the right. So if we want to provide coverage in just 45 degrees, we can see that the sector just vastly is much, much better than the horn. There's a big gain improvement. I have this chart down here, about 4 dB. Now, if we look at the edge of where you're using the sector at plus minus 22.5 degrees, that's the edge of your coverage. You can see the sector is still at 17.5 dBi gain, where if we go compare it to, if you wanted to use the horn, you're at 10.2 dBi gain. That's a very significant drop. You can see it's the 6 dB roll off from the max gain. So you just have to be very careful in how you're using these, because you're going to see a lot less signal strength if you just pulled out a sector of the same beam width, or you thought it was the same beam width and put up the horn. Even though it's smaller, get a little bit less wind loading, you're going to have that issue where the gain's dropping. You might lose a few customers. The true comparison is against the 60-degree horn. You can see here that the 3 dB beam widths are roughly equal, but the caveat is that the gain dropped significantly from 20.5 to 13.2, and then the gain on the edge is about the same as the 40-degree horn, but compared to the sector, it's a 7 dB drop. Now, you might be thinking, well, why did I go with the horn? Like I said, wind loading one. Another thing touted a lot is the side lobe levels. But if we're actually comparing apples to apples, side lobes, like I said, you have to compare the 45-degree sector to the 60-degree horn, which has the same 3 dB beam width. Look at the red curve and the green curve. They're almost the same. In fact, the 60-degree horn has a higher side lobe levels for large angles. So it's kind of just showing you that when we're doing these comparisons, talking about side lobes, you have to actually do the comparisons properly. Now, naively, we'd compare it to the 40-degree horn, but it's just not even the same antenna. It's like comparing a 90-degree to a 45-degree. It's just that much narrower beam width, which obviously causes the beam to be much narrower here for large angles. Now, what does that mean on the ground? Well, this is a comparison over pretty ideal terrain. It's pretty flat farmland in Alberta, but comparing a 40-degree horn, 60-degree, and the 45-degree sector. Now, the sector you see just overshoots everything because it's higher gain, massively higher gain. But one thing we should notice here is that close to the tower, a little bit hard to see here, if we compare a 45-degree sector to the 40-degree horn, This is very focused here. You're not going to pick up people at large angles, even very close to tower. Where here we're actually picking up a few more, a little bit higher field strength here, and also here that where it says Hollis, we're getting better coverage there, and on the edge of the S, where here with the horn, you're not picking up that Hollis and then the S right here. So it's you could kind of see that the beam width is very important. The 6 dB roll off on the horn is causing you to drop a lot of clients. If you had them in that region. Now you could say, oh, I'll put more horns up, but you're at the same cost as the sector antenna. So it's one or the other. Now I'll do this comparison again for the 60-degree horn, but it's just a repeat of what I just said. Our 60-degree sector in the ProLine is very well designed. It's almost equivalent to the same beam width horn, which is, like I said, now it's a 90-degree 6 dB roll off, but if you compare the 3 dB, it's actually 60s, 65s. But you can see we're very similar to that horn. At the same time, we have better front to back ratio. So you can see the front to back on the horn actually picks up a little bit, where with the sector, it's 35 constant. So it just goes to show that just because the horn's smaller, that they look more sleek, that once you get in the field antenna performance, sectors are usually winning the day. Now here's a study that was performed by Mimosa. It's a propagation study they did comparing this 60-degree horn to a KP sector. It's one we've sold for many years, and you can see just the vastly improved coverage on the edges of the sector, and that's just what, like I said, because of the roll off on these horns and also the less gain. Now, same thing with 90-degree. I'm just going to quickly skip that and talk about the asymmetric horns. These are newer products, and oh, apologize. These are newer products and touted as being equivalent to sector antennas, but once again, we have to make sure the comparisons that we're doing are proper and fair. So, and I apologize, this is actually comparisons to the 60-degree asymmetric horn, not the 30, because the 30 would just be a little pencil beam here. But you can see here the 60-degree horn, and I'm going to go down here, has the same azimuth beam width as KP's 45-degree ProLine sector. And say azimuth. So this is a really apples to apples comparison. The only difference here is the elevation beam width of the KP sector is 6 degrees, whereas the horn is 17. And of course that comes from the increased size. But the benefit is the higher gain. We have a 4 dB higher gain. And that's, they might be even more. We haven't done the cook off in the field, but you could see that now going back up here to the upper right, this higher gain here is just going to do so much better in our coverage area of 45 degrees. At the edge of the sector, we're still at the 45 plus minus 22.5 degrees where we're using the sector. We're still 17 dBi gain. That's awesome. And whereas the horn, and sorry, this should be reading 10.2. And I got to proofread these. But another thing you take a note is the front to back. On the sector, it's 40 degrees, whereas this horn, it's 27. You're going to run into maybe a few frequency reuse issues if you put two of these back to back, or you're going to have to increase the spacing or put shielding in. Whereas the sector, they can be pretty close together with 40 dB front to back, and you don't need the shielding at all. We spent a long time optimizing this design and the side lobes of it. You can see that the side lobes of ours comes down nice and sharp here. Whereas the horn, it's a little bit broad. This is kind of a typical pattern that I see all the time. And it's at 90 degrees, you're sitting minus 25 pattern level, but then with the KP sector, you're well at minus 30. So this is the comparison we should be doing. Always look at the beam width on the data sheet and the definition of beam width when you're doing these comparisons. I mean, the asymmetric horns are just like sectors. That's all they are, except they're wider elevation beam width sectors. Because I mean, you can't look at how much metal's involved. You can't make them like as wide, as tall as a sector, because just the cost would be increasing. And here's another comparison with our KP 60-degree sector versus the 60-degree horn and 90-degree horn asymmetric. And you can see everything's kind of overlapping here. The only one that actually has sorry, going back to the left here, better patterns is the 60-degree asymmetric horn, but its beam width is a 45. So it's not an apples to apples comparison there. And if you wanted to use this as opposed to, you know, the 60-degree asymmetric horn as opposed to the 65-degree sector, you're going to drop off a lot of clients right here. This is a huge difference between these two. So it's kind of just showing that that once again we have to be careful in how we're choosing our tools and making sure we don't discount, you know, the tried and true technologies from the past. Even though something's new and sleek, you might be running into some unexpected issues. Another thing I like to point out is the front to back. Once again, the sectors just do awesome. A lot of that has to do with how we design these sectors, but also its size helps the front to back too. So it's anyway, but every tool has a use, as they say, and I think sectors are primed to still be popular tools in our market. Now here is just once again a coverage map between the 90-degree, 60-degree, and the KP sector, comparing the asymmetric horns, and we reach farther out, same region that we're doing these plots on. Now, new products. This is really cool product that we introduced actually at the Wispapalooza show. We had one up in our booth if you had a chance to see it. And we worked closely with Cambium to develop, it's a 4-port, 5 gigahertz Omni slant polarization that's capable of utilizing multi-user MIMO performance on the uplink. Now, we worked very hard with Cambium over a year to design this antenna. And what we ended up coming up with was this very unique design. You might say, oh, this kind of looks like Mimosa, but a little bit different, where we take, if I open this up, it's pretty much 4 sectors in there, but the 2 sectors that are back to back are connected together. That gives you this nice bidirectional or dipole-like pattern. And then on the opposite side, we have the same thing. And I'd go into the differences with Mimosa, but theirs are summarized it's just 4 sectors where each port on the antenna is just 1 sector, where this is 2 ports correspond to up down and 2 ports correspond to left right. Now through the magic of multi-user MIMO and MIMO in the Cambium antenna, these actually overlapping patterns add up together, and it gives you this omnidirectional pattern that we see here, where the pattern or the strength is really close above 3 dB for most of the angles. So this gives you, you know, pretty good coverage, you know, anywhere from, I'd say, in ideal terrain up to 5 miles. It's really going to depend on, you know, where you mount it, how high, and what it looks like around. But you know, 2 to 3 miles is going to be I think pretty easy to achieve. And this is an exciting one. We're hoping for release in January 2020. So just watch out for the email on this one. Now, we did release in the meantime an antenna that we knew very well how to build. So we released this already. It's in stock. And this is a 4-port 5 gigahertz Omni, but it's H and V polarization. Same game, 13 dBi. But what we did here was we vertically stacked 2 Omni arrays in a single radome enclosure. And then so it has the 1 mounting point, but the 4 ports. So you can use this with, you know, a 4x4 MIMO radio like Cambium, or not Cambium, sorry, don't say that. The Mimosa A5C, or you can use 2x2 MIMO radios. I mean, you could use it with Cambium, but don't expect multi-user MIMO to be working. So this is, it's very similar to how we construct our 5 gigahertz 2x2 Omnis. So what, you know, it's not too much to discuss here, but if we have some questions on it, I'll gladly answer. Another new product that we released is our new 11 gigahertz ProLine parabolic antennas. So we released a 2-foot and a 3-foot dish that goes with we have an FX, so one that goes with the Ubiquiti 11FX, and then one that goes with the Mimosa B11 direct connect. So here's just 2 images of it. And these will be the 11FXs. I think you can acquire about them. The 2-foots now, and the 3-foot should be by the end of this year. I'll follow up with Mike or myself on the availability of these antennas. But you know, very well constructed antennas. They're fully assembled at the factory, which kind of simplifies your installation. It's going to be quickest time to tower. You know, comparing this versus a competitor's antenna, you're going to 1/4 or even 1/8 the amount of time it takes you to install this. You're not assembling all the piece components anymore. Another benefit is because we install it, you can be guaranteed of its performance because we install it according to our assembly instructions, and it's reliably done the same every time. So the FX is a direct connect N-type version, and then the Mimosa is a direct connect with a waveguide interface. Very well constructed, very good tilting features on it. So I think you guys would be very happy to deploy this into your network, and also reasonably priced too. So very competitively priced to what's on the market right now. And here's just a sample mass. The side lobes on this are just outstanding. You're meeting, your Cat B compliance for the 2-foot, and then the Cat A for the 3-foot, and then ETSI Class 3 if any of you guys are in Europe on the 3-foot, and Class 2 on the 2-foot. Dual band OMNIs, we've had these out for a while. Just briefly, what it is we take 2 OMNIs and we vertically stack them in the same case, run the cables down all the way to the bottom. So you have 2 ports for each band. So 2 ports for 2 gig, 2 ports for 3 gig. And then we did the same for all the unlicensed bands. So 2 gig, 5 gig, and 3 gig, 5 gig. And very similar gain to what you have for the single band. We saw they're a little bit taller, of course. But we have many of these out in the field already. And here's some client testing we did. And what he did was he pulled his old 2 gig Omni off and added this extra, the dual band and then the extra 5 gig band. And he saw a very similar strength with his 2 gig Omni that he had before, plus or minus 2 dB in the transmit and receive. He was very happy with the intent of the customer A. And then Watch Communications, they replaced the 2 gig Omni and the 5 gig Omni and put this up, and saw very similar strength, plus 1 dB gain in the transmit and receive, and they're very happy with this antenna. It's still up. And this is just some metrics. We don't really need to go over this, but it just kind of shows that here's the 2 gig Omni. Let's just look at section 8 here. 2 gig Omni and minus 56, minus 61 transmit receive. And once they replace with dual band, they're very similar strength here, minus 57, 58, 54, 58, and they're able to have their high modulation rate on each frequency. Now, this is a very cool Omni. It's the Canon, as we like to say. It's a 2-port slant polarization 900 megahertz dual pole Omni. Covers 824 to 928 megahertz. In fact, it actually covers even the higher unlicensed bands we're finding out. So if our higher licensed bands, so up to 1 gigahertz, this antenna supports up to. But really, we designed it for the PMP 450i 900 megahertz AP radio. It has very nice Omni pattern. This is good for if you want to provide coverage, anywhere 3 to 4. 5 miles, you're pushing it. You're probably going to pick people up and modulation will drop, but it's very good for penetrating your dense foliage, and in case you have very high canopy, or some people even mount it below the canopy if they have issues with interference with other 900 megahertz equipment out in the field. But it's still it's a very awesome antenna, and very well reasonably priced and in stock. Did field testing. Not gonna go over this too much, but like I'm saying here, that this client, he was in Ohio, Southwest Ohio, rural farmland, some tree lines, some ravines, using the Cambium 450i, about 27 dBm power, center frequencies 915, and then on the CPE side, he's using our 14 and 17 dBi Yagis, and he was at Gable. You get out, 5.2 miles, still decent signal strength, minus 71. I think I have one more chart actually, which better shows this. Yeah, right here. So this is kind of what they were seeing here. So they're getting very good signal strength out to very far. He wasn't trying to pick up lots of clients with it, but just the handful, a typical Omni application, and serving your cap funding required download uploads. And so, yeah, this was, he was very happy with this antenna. He bought multiple ones of them and put them in many different locations because it's a very cost-effective solution. You don't have to buy multiple APs at 900. A lot of people still love 900, even though it's noisy, but certain areas have different noise characteristics. So it really is just choosing the right frequency for your application. We released in this phase 2 a dual pole 120 degree sector. It's a little bit big, but it's the big comes with gain. So it's 12.5 dBi. Very high gain, very high performance antenna, good front to back, uh, and you can put 2 up on a tower and get really good coverage. I mean, if you look at the intersection right here, this is about -8, let's say. So that means where they intersect, the gain is going to be about 4 dBi going at the two directions. And what you do is maybe you choose those two directions where they meet and it has least signal strength. You put that in the direction of the least clients or the closest clients or no clients. And then the next upgrade path would be go to 3, and 3 provides much better coverage, and high. You get out pretty far with this setup. Now, another area that we're excited that we just got into last year is the TV white space. A lot of hype on it with Redline, Radwin, and then the old players too. But we released 2 sector antennas, one Yagi antenna and a flat panel antenna. So the sectors, which I'm showing here, we have a dual pole version, a 65. They're 65-degree beam widths, 12 dBi gain. They're not the big monsters you see some suppliers have, which they use one more element than us, but we have roughly the same gain anyway, just because we're using a very high performance element. So I think we chose this size form factor because it's a compromise between the gain and also the shipping. If the ones from some of our competitors, they're a little bit too big to fit on a pallet, and you're paying over shipping charges for that overage of the package size. So this is a nice, very cost-effective solution at this frequency, and it has the built-in GPS antenna here. So that means on the dual polarization version, there's 3 ports, one for each polarization, then one for the GPS. The GPS just sits right at the top there, and it, works great as opposed to using one of the external GPS antennas. Now we also have the direct mount option ready for the Redline 3000 XP up lips. That's the Redline AP, and then the first gen CP too has the same form factor, and that just sits nicely right here on this square plate. As more radios get released, we're working with Radwin to kind of make a direct connect option for their antenna or their radio, and also if Redline revs their radios, we'll also work with them to create more direct mounting options. So here's the dual pole Yagi. Everyone's really liking this Yagi because typically if you open up and I have it in front of me, the maybe just the white paper on the TV white space. On the CPE side, you see these massive antennas. It's usually either 2 log periodic antennas, or it's or a big panel antenna, or maybe a little panel antenna, but it has really low gain. So this is an alternative to using 2 log P antennas that take up 10 inches of height or 10 feet of height and 10 feet of length off the pole. It's a nice small form factor. It's about the same size as our 14 dBi Yagi, so I think about 3 feet, 2 to 3. I think it's 3 feet, and dual polarization too. So now instead of 2 single pole antennas, you have this one dual pole antenna. You just mount this on it on the house or J-arm, and you're good to go. And one of the neat things about it is that you can rotate the pole, so you can rotate the angle of the dipoles and the directors, such that you can optimize your signal strength. So like I said before, once things leave the antenna, it's no longer true 45 or H&V. It's somewhere in between, so you can just rotate it, tweak it till you find that sweet spot for that particular location, and you leave it there, and now you have very good signal strength. Whereas some other antennas, you're kind of fixed in the polarization you can do. It's also very lightweight. It's using 6061 aluminum. So that's a very high grade of aluminum, compression crimped elements, and then painted black. So ice buildup is going to melt off very quickly once that sun hits it. Here's a flat panel, TV white space flat panel that we just released. Very similar gain to the other one. You're going to get a little bit higher gain depending where you are in the band. But it's nice small form factor. It's about 3 to 4 inches deep. I think it's 13 by 13 inches, and very robust bracket. It also has mounting for the Redline radio, direct connect, so you don't have to use the brackets. You can just use this Redline radio. We've performed a very high level of testing to here, so it's very corrosion resistant. Wind loading, we went and you can see here we loaded up a very high weight on it just to see if it'll support ice buildup and also the wind loading in different orientations. I'm surprised it did. Not really surprised, but it was a cool talking point at the water cooler. And yeah, very nice front to back and side lobe suppression. So it might help if you're in a noisy area to help reduce that noise level a little bit more. And we did field testing in the winter with one of our very friendly clients, where we compared the Yagi, the existing 11 dBi single pole Yagis, 2 of them, to our dual pole panel and the competitors panel, and then also our panel. And yeah, so the testing conditions was, like I said, winter, winter tree foliage, and then looking at 1.5 to 3 miles. It's very far from the 40 plus miles touted by TV Whitespace, but due to noise restrictions and the power restrictions and height, this is, typical deployment is less than 5 miles, I would say, unless you're in some ideal condition. So comparison, this is all baseline against the 11 dBi single pole Yagis, 2 of them. They pulled them down, put up the red line 11 dBi panel, and they saw pretty much no change, maybe plus or minus 2 within base. Now they put up a competitor's, it's a smaller panel, it's an 8 dB panel, and they saw the signal drop by 3 dB consistently from the base. The QAM rate dropped as a result, and then the latency and jitter was roughly the same. Now they put up the KP 9 dBi panel, and the center dropped about 1 to 2. It's kind of expected. I mean, a 9 versus 11, of course, that means the gain's going to drop 1 to 2, or the signal strength. But the QAM rate was still comparable, so we're still, above the noise floor on the downside. Now, center up, we saw 1 to 2, and it reduced the QAM a little bit. But I mean, yeah, it's kind of funny. You see it one direction versus the other. There's some everything's not bidirectionally symmetric. Now on the Yagi, they're very similar comparisons to the actual 8 dB panel, and the QAM rate was very similar too. But the benefit here is that like I said, they were able to adjust the polarization a little bit and get a much better signal overall. So leaving TV Whitespace and going to our parabolic dishes. So we have these parabolic dishes. They're very, very popular now. They're really taking off. And the reason is because they're so well constructed. So we have the 1 foot and 2 foot dish that covers 4,900 to 6,400 megahertz. The 1 foot dish is 24 dBi. The 2 foot dish is 29 dBi. And that's like the lowest gain. If you're up in the high part of the band, you're going to be at a way higher gain. And the reason people like it, like I said, is the construction. This very high grade aluminum, that the powder coating we're using is very, very well done. The brackets are very strong, and the people like the how we're doing the adjusting on the tilt and the azimuth and elevation. And we also have a remote option to mount mount the radio directly to the back of the antenna here, using just a hose clamp. So people have, they pull out a competitor's dish, lower cost competitor's dish, they put it up ours, and they see, vastly improved signal strength. One client, he had a let's just say competitor's antenna up, and his signal was dropping every once in a while. It just wasn't consistent, and it was a 28-mile shot, I believe. And then he put up our 2 foot dish, and it was just very constant, reliable, getting good signal strength. The other benefit here is the side lobes on the KP dish. We worked really hard to suppress the side lobes and get very good front to back ratio. So the front to back on the 2 foot is 40, and on the 3 foot it's 35. Or sorry, on the 1 foot it's 35. And the side lobes, I mean, doesn't mean much to you guys, but they're meeting at a minimum ETSI class 1, and then very close to ETSI class 2 for the 2 foot. So it's just vastly reduced side lobes will help you reduce the amount of interference you see on it, and give you a very, very good link. So these are available today. We have 2 versions out. We have one with the N-type connector, one with the C5C. We're about to release one for the ISO station. That's a little circular ubiquity thing, and then the M5 and all the variations with it. We ran into a few issues in prototyping, but we're there. So this is kind of what the antenna looks like. And then there's an optional radome that you can get as an accessory too. One of the very neat things that we have a patent on is the quick connect. I'll show you what it looks like in a second. So, I'm just going to skip over this because I talked about all the very cool properties of this, but very flat performance across the entire band. That's very tough to do from 4.9 to 6.4. There's just to geek out a little bit, there's a mode that an extra mode that gets excited at 5.96 gigahertz. That's the higher order mode that ends up screwing up the VSWR, the port isolation, the gain, but we were able to suppress that in our design. It's not an easy feat to do. Now, yeah, I talked about interference mitigation. So this is, you're going to be able to, place these maybe two side by side if you wanted to. I would maybe not recommend that, but at least two houses very close to each other, not worrying about them talking to each other too. And that has to do with how deep we made the dish and also how we designed the sub reflector, which is the piece in the middle here that's on the end of the feed. Yeah, heavy duty construction. I'm not really going to get into this, but people are not having any quality issues on these now. So we're really happy with the design. You can see all the screws here. We might reduce the number of screws a little bit, overkill on the 1 foot, but we did that just because we wanted a nice, safe design. Here's a little video of what the quick connect technology is, and really it's a coupler system that allows you to quickly pull out the feed horn or pull out the adapter to allow you to replace it. You can rotate the adapter 45 degrees. If I go back just to here, yeah, this image right here, you can see we have these markings here which tell you, okay, when the port aligns with H, that's H, when the port aligns with V, that's V, but you can rotate this 45 degrees so it's slant. So you have that flexibility in buying one antenna that'll work for different types of AP radios, different polarizations. Like I said, though, at the beginning, the polarization mismatch is not a big issue, but obviously you want to match it as much as you can to get the best signal strength. Now just going back to here, another benefit of this is how we package this and get it assembled. So this is almost fully assembled in the box. All you do is you quickly slide on the feed horn and the adapter, and then pop in the dish. It comes attached to this piece right here, and you pop it into the brackets and it's done. You can install this in about 3 minutes flat. So that it's just simplifies the install for if you have any third-party installers doing it for you. Just reduces your cost to them by having them in and out very quickly. And like I said, we have the N-type version and also one for the Mimosa, not A5C, the C5C, and we have one for the ISO station coming out very soon. And we're working on more as we speak too. Yeah, so just great antenna, mounts different sizes of pipes. And yeah, now back to sectors. So we have our small angle sectors. Guys, these are really very well designed sectors, very small beam widths to focus your power, and then that little area you need in case, let's say you're going for densification or you just want to serve that little area. These are great antennas that'll have very high gain, very low side lobes, very good front to back. I mean, the front to back on these are 35 to 40. And if you compare them against some of the very few in the industry that have similar beam width, apples to apples, the side lobes are much less than ours. One of the reason here, let's look at 3 gig. If you compare it against the competitors, we target a little bit higher band, 3.5 to 4.2, where competitors go 3.3 to 3.8. The benefit of doing this is because we start a little bit higher, in the CBRS band, the side lobes don't start creeping up until you hit around the 3.8 to 4.2 mark, whereas the competitors, it starts hitting at 3.5 to 3.8. So it's just because the design we chose and also how we targeted frequency, we get a much better side lobe design. And then for 2 gig, we actually targeted 2.4 to 2.5. That's unlicensed, that's our space. Whereas our competitors will target the entire band and optimize the entire band, where we just optimize that sub band the most, 2.4 to 2.5. Fixed 4-degree down tilt. Call us if you have a 0-degree down tilt option, and we can talk about lead times. But typically this is the best, And if you want to reach horizon, you just tilt it up a little bit. You're not going to have any issues with that. The brackets kind of allow you to tilt up. Yeah, universal radio bracket comes on all our ProLine sectors. Can't really see it here, but it goes on the back. I don't know if I put a slide in here. We were cutting slides like mad, but it allows you to, mount directly most radios, and not all, but most radios, your most common ones, your cambiums, ubiquities, directly to the back of this antenna. Oh yeah, and here's the patterns. I mean, it's just beautiful what's happened here. very, very low side lobe levels. If we look at how they overlap, maybe we want to do a frequency reuse 2 scenario, the overlap is very minimal. I mean 25 dB once you're in the next sector sharing the same channel. So if you have good separation between those sectors, you might be able to achieve this very, very easily. And then our 5 gigahertz sector, it's just awesome, 45 degrees, very low side lobes. There's not much like it on the market. I think this is the last slide on the new antennas, but this is our whole lineup of ProLine sector antennas. We also have our standard or commercial line sectors, which cover, pretty much a lot of different bands, or not a bit different bands, but different combinations of frequency and beam widths. Your 120 degrees, your 45, 65s, 90s, and different dual band option. But here is the ProLine sector. They have this great construction where we optimize the side lobes front to back, flat gain across the band, ultra wide bandwidth. And the newest one we released is this one right here in the dual band. It's a 2 gig H&V, so H&V polarization on 2 gig, and 5 gig H&V polarization, 8-port version. We have a 4-port in our commercial line too, if you just want to do 2 by 2 on each band. But this is for your new radios coming out. Let's say your EPMP 3000. I'll show you kind of which radios would pair with this. But we also have a slant version here. And we have a 4-port and 8-port version. The 8-port obviously didn't make the cut on this sheet, but lots of different options available. Inquire with us on what your needs are. We'll direct you in the right direction. And yeah, let's just keep going. So like I said, on these new 8-port radios, which radios do you put on them? New 8-port sectors, which radios do you put on them? And I'm going to be finishing in 2 minutes, so we can do questions. But you can put any 4-port radio on the 5 gig side, or any 4-port radio, or 2-port radios on the 3 gig side, and you can do 2-port radios on the 5 gig. So some Prism ACs, put 2 of those, or Cambium PMP 450s, or the 3000. And then on the 3 gig side, you put maybe a Telrad or Bicells 233, or the Nokia. This is an awesome radio, or the Ubiquity Rocket. Some of the older generation radios, but just lots of different combinations you could do here. And then same with 3 gig and 2 gig, pretty much the same radios, just different frequencies. And just allows you to think of how much capacity you can get with this 8-port sector and 2 radios, or 4 2x2 radios, or 2 4x4 radios. It just allows you to have that single mounting point of the sector, reduce your tower loading and also your rental costs. Same here. Nope, there we go. 2 gig, 5 gig. So this is very similar. You put the Prisms or the Cambium EPMP 3000 on the 5 gig side, or Mimosa, and on 2 gig side you can do your traditional ones, Rockets or Cambiums or Bicells or Telrad. You won't be mounting all these radios directly on the antenna. Only one radio will mount directly on the antenna, and then everything else can just be pole mounted below or above the antenna, or directly behind. Reduce your cables. So typically the connectors come out on these ones near the bottom on the backside. I don't think we have time to go over this part. I'd like to really get to the questions, but choosing your sector is very important. How do you choose it? You start with the 360, and then you go down to 120s and 90s and 65s. But how many we go around the tower really depends on what type of technology you're using. Is it LTE, Wi-Fi? What is it? Because the noise level that is required by the radio will definitely determine how you can reuse frequencies around the tower. And you only have limited spectrum space too, especially at some of the 3 gig bands and 2 gig. Yeah, I don't have much time to go over this, but a frequency reuse 1, 3 sectors, 65s, that's what you have to do. You won't get away with 4. It's just impossible. Frequency reuse 2, 90s back-to-back, 45s back-to-back, 8 45s, 4 90s, and or 65s back-to-back 4x4. This is for LTE because of the interference you get. You want to minimize it. And I'm just gonna skip over there, and this is our last slide. So Infinite, KP is part of Infinite Technologies, and they own a number of different brands that you may be familiar with. and we can support you in all of them. So if you have any questions, reach out to the KP team. If it's either protections, transector and polyphaser for your surge protectors, or if it's backhaul radios with radio waves, or some cables, or something from Elcom, whatever it is, we can help you out. So thank you very much for your time, and Angela, I think we can open it up for questions.
Yes, we'll wrap up with some questions. I have a question here that's asking, on the 5 gigahertz parabolics, you have 1 and 2 feet antennas. Are you coming out with 3 and 4 feet?
No, KP is not, but if you want a 3 or 4 foot antenna, Radio Waves has an excellent antenna. It's the HB, depends if you want a high performance or a standard performance, but it's the SPD 3-5.2 NS or the HBD 3-5.2 S or the HBD 4-5.2 S, SPD 4-5.2 NS. So our sister company Radio Waves has you covered, and we in the near term don't have plans to do a 3 or 4 foot.
Okay. What are the advantages of the ProLine parabolic antennas?
Yeah, so I think the main advantage, at least to me, if I go back to here, is the pattern performance and the gain. Even though the gain looks very similar to what you see on competitor spec sheets, like I said, once you're in the field, the gain is actually about 1 to 2 dB higher. I won't say compared to who, but we've heard anecdotal evidence of this, multiple times that the gain of ours is a little bit better than the competitors, about 1 to 2 dB. But it's the pattern performance, I think, which really shines it. We spent a long time optimizing the side lobes. I think we went through like 11 different revisions of this reflector design and feed horn design, just to optimize it across the band as much as we can. So you're going to be picking up less noise on this and get more consistent signal strength. So anywhere in your noisy environments, this will do well.
Okay, great. We'll end it with one more question, and it's, do the ProLine sector antennas come with a radio mount?
Yes, they do. And you know what? I wish I had a better picture, but there's a radio mount that gets slotted in the back here. Yeah, I can probably find the picture, but it's a radio mount. It does come with the antenna. Just
okay, great.
Yep.
Thank you. And that is all the time that we have. As I said earlier, that this webinar has been recorded, so we will share that with everyone that attended today. So keep a lookout on your email sometime this week, and we will also post it on our YouTube channel. I want to thank KP and everyone attending, and Justin for a great presentation. And as he mentioned, any questions, please reach out to Streakwave and KP, and we'll gladly help answer those. Any last remarks that you wanted to add before we hang up?
Yeah, just kind of drive home the point of the horns. When you go back and purchasing, or whoever your engineer looks at them, make sure they look at the beam widths and the definition of beam widths is very important. And also these asymmetrical horns. Take a look at the KP sector. It's you'd be surprised what it can do. We'll share the pattern files with you if you want to do a comparison. And I'm sure you can talk to Mike, and he might be able to get you a sample if you if he likes you. But yeah, it's these ProLine sectors are just very well designed, and I would say they're on par or better than the horns. So that's my closing remark.
Awesome. Thank you. Thank you, everyone. Have a good day. Bye.